Welcome back to OCR MEI Further Mathematics B. Today we're doing Chapter 9.2, First Order Ordinary Differential Equations. So ideally, there are two main ways of doing first order ordinary differential equations. The first one is separation of variables, which you have touched on before in normal math. And the second type, which is the one that we're going to talk about this video, is the integrating factor method, which when you see inseparable or aseparable, whichever that word is supposed to be, differential equations, then you can try using that as a method. Let's first of all write down the general shape of the first order differential equations that you can use this method on. The general form is, let's see, I'll use x as our variable, x dot plus px equal to f of p. Actually, this is a terrible idea to write. Let's see, why don't I use this instead? Y dot plus a function of x of y equals to a new function of x. So y dot plus fx of y equals to g of x. This whole thing looks complicated, but in order to carry out the integrating factor method, it's essentially just a method for you to remember. It's kind of pointless to it's kind of pointless to know exactly how it's derived, but it's important to know why it works. So let's try to break that down. So first of all, I'll show you the method that you need to know, then I'll run backwards to show you why it works. So the method is to look at this function of x, and we can state that an integrating factor r, or some textbook use I think mu, so a symbol mu. I'm not sure which one the spec uses. I'm gonna stick with the r that I'm used to. So the r, integrating factor r, is e to the power of an integral of said function x, which is the coefficient of y. And with this, we can say that the left hand side will go into d by dx of yr equals to g of x times r. And from this we know that actually I need to state the dx over here. So from this we can deduce that r is a function of x, and now we have a function of, we have a function of x on the right that we can integrate by dx on, and that wouldn't be any problem. So we get that yr is the integral of gx r dx. And with that, we have this extra r that we divide, and we're left with the solution y equals a function of x, ux, let's say. So this whole mess works because of this conversion. And in order for this to be true, we first multiply the top row by r such that we get r y dot plus r y fx, and actually that's fine as is. And if you differentiate this yr term by dx, we can get something in the form using implicit or chain. I think it's no, actually use product rule, my bad. Just keep forgetting these rules. So y dot times r add y times r dot, and r dot let's see, r dot in this case would be f of x e to the f of x. Wait, actually no. Let's see. This is no, not accurate. Let's see. Is that differentiate? This gives me fx e to the integral of fx dx, which is fx of r. Fx times r. And turns out that if you sub this into y r dot, you get the same expression as the top. And so you're allowed to do a conversion from this to that. But because you have an extra r as a term, then you need to multiply the right hand side by r as well, so hence this r over here. First order is a bit when you first start, it's really quite confusing. So let's talk about, I'm gonna show you a solid example for how this actually works. However, do remember, after you integrate, you do need to add a c, and that would be a c on r, because the c is added on this integral. Then we divided everything by r, so this r is important. So yeah, I'm gonna give you a solid example before I ask you to do any questions. Alright, so I just made this question up, therefore the solution wouldn't look anywhere nice, but it's fine as is. So let's have a look. Let's see. First of all, we find the integrating factor r, which is e to the integral of x squared dx according to the coefficient. And this one, fairly simple, is e to the x cubed on 3. And the plus c on the integrating factor can be ignored for some reason that is not explained. Then we have this whole thing, and we can multiply in everything such that we have e to the x cubed on 3 dy by dx add e to the x cubed on 3 x squared e, well, not e, just y, equals to 5x cubed e to the x cubed on 3. So last example, when I did the algebra, I used y dot rather than dy by dx. Technically that's okay as a notation, but it's better to use the dot only for dt, which I forgot about because I'm just lazy to write the dy by dx expression. But when you're doing it, then try to use the proper notations. And with this multiplied r, we can just state that d by dx of e to the x cubed on 3 y equals to 5x cubed e to the x cubed on 3. Well, ain't that troublesome? Can I integrate this? Oh, this might not actually be a good thing. Yeah, I should have checked. I should have. I can't just make up differential equations. Now that I think about it. Right, this is gonna look bad, but I'm gonna keep the integral because just by looking at it, I don't think it's integrable. Do let me know in the comments if it is integrable. But for the purpose of the demonstration, I'm just gonna keep this whole thing in integrals and work my algebra. I'll make sure I'm just gonna take some old past paper questions for differential equations for you to do for the purpose of the question section, just in case I did something like this and goofed it up. So we have e to the minus x cubed on 3 multiplied by the integral of 5x cubed e to the x cubed on 3 dx. Make sure you have the dx, by the way. So that would be the solution, which is unbound. So it's not a... Okay, I need to talk about terminologies here. So after you've done all the calculations, you will end up with a solution with a plus c after you break the integral, that is. This whole plus c madness can be commonly called, the whole expression can be called the general solution, GS. So this y is the general solution, this whole polynomial is the general solution of this differential equation. And with that, we can actually apply a boundary condition, which is saying if I have y equals to 0 at x equals to 0 and y is 3 at x is 2 or something like that, then actually no, y dot normally it would be, yeah, so it's normally something like this. Then you can just substitute in the expression for 0 and 0, y and x, and you can get some polynomial expression which wouldn't be enough. So you will need a... Actually, wait. this is a first order, so you do not need this. You do not need the second bit. For second order, however, you do need that. Yeah, basically, if you apply the boundary condition, then you can solve for C, and you will be left with a solution which is called a particular solution. Yeah, basically that's it for first order DE. And yes, it's kind of confusing, but for DEs you will just have to learn a lot of methods and try not to question too much, although questioning is normally a good thing. For DE, it's better to kind of learn how to do it, practice a lot, then kind of understand how it functions as you go along. Right, so differential equations, you will need a lot of practice to get good. And given that it was used to be an entire module in the previous A-level spec, I do feel like this is a very big hurdle for a lot of people. And there are a lot of cases that you will need to know how to deal with without like getting confused or anything like that, which is difficult to handle, but it's still manageable, I guess. So yeah, basically see different types of DE questions. Make sure you understand what you're doing and follow through with the method, then you should be able to get the correct solution, given that your algebra is perfect, which for most of us aren't. Okay, so I got you January 2007 past paper, and this is from the DE paper, question 3. I want you to try this section 1 because you can practice your integration factor, and also you can try to formulate your equations using the knowledge I've given you on part 9.1. You can probably work on this a bit. I think for the physicists amongst you, it's gonna be really easy because this is basic mechanics. However, I guess this part would be also quite easy for the ones who would take the mechanics major module. But for the ones who managed to avoid all the mechanics, then I'll just have to say good luck, because it's gonna be tough. Yeah, although formulating is important, so this whole dv by dt equals to g take k1v, this expression is important. However, it's not really devastating if you can create this from the questions, because it's given to you, so you can always attempt just the hence show part. So use this expression, do your integration or separation, and you should be able to get an expression like this. But for now, I will give you 5 seconds. Well, turns out I'm pretty silly because it's a show that, so there isn't a solution. Well, the solution is given anyway, so you can just work on aiming towards getting v equals to g on k1 times 1 take e to the minus k1t. If I have to say how you should do that, it would be to apply your boundary condition, because I think it's released from rest. So t at 0 would give a v of 0. So use that, eliminate c, and you should be able to get that expression proper. So yeah, basically that's all. Thank you very much for watching. I know there will be a lot of questions surrounding DE, so do let me know in the comment section below. These videos will start to get a bit more lengthy starting from the next video, because it's second order and there are a lot of cases to cover. So yeah, thank you very much for watching, and I will see you on my next one.